So in this lesson, we'll be looking at the exterior angles theorem and angle sum theorem for 4.04 exit ticket. Starting with our warm-up here, I want you to identify if it's a polygon, how many sides, what's its name, and is it concave, convex. So one way that you can illustrate that is you have 1, 2, 3, 4, 5, 6 sides as well as vertices, which you can count them up, of course. So we know that it's a polygon because it's closed and because there's at least 3 segments that all are connected. Every segment only intersects another segment at its endpoint. And so because of that, this is in fact a polygon. It has 6 sides, of course, as you can see. And a 6-sided polygon is known as a hexagon. Also in this case, you can see 2 vertices are pointing inward, meaning that there is a cavity as well, so we know that it's caving in, so that is a concave hexagon specifically. Today, what we're going to do is we're going to prove the angle sum theorem for triangles and prove the exterior angle theorem for triangles. And then we're going to solve problems using the angle sum theorem for triangles and solve problems using the exterior angle theorem for triangles. Specifically, we're going to learn about the triangle angle sum theorem, practice problems, learn about the external angles theorem, and practice problems, and then we'll refer to the exit ticket as well. Now, in this case, in the video, I'm not going to actually go through or show another video within a video, but instead what I'm going to do is I'm going to walk you through a proof of the triangle angle sum theorem briefly. So imagine you have a triangle right here, and we have the angles labeled A, B, and C. So we have A, we have B, and we have C. What I can do is I can construct a segment which is going to go through B, and also it's going to end up being parallel to the segment AC. Okay, so not quite drawn to a parallel relationship, but we're suggesting that there is a point or a line that can go through a point that is in fact parallel to the bottom segment as well. Now, the reason this is important is because right now we have measures, which I'll just color code, green and orange and blue. In parallel lines, we know that if you have a parallel line pair like this, and you have another line that intersects those two, sometimes we refer to that as a transversal. And this creates a special angle relationship between this angle here and this angle right here. That is referred to as alternate interior angles. So what that means is if you have 2 parallel lines, which using these 2 arrows that represents 2 parallel lines, this angle down here is the same as this angle right here. So angle A's measure is also equal right here as well. Likewise, we can also see the same exact relationship with this angle here and this angle right here, because that's also alternate interior as well. So the reason why that's important is because I want you to pay attention to what this is actually forming right here. There are 3 angles now that represent that. And for the purposes of just using A and C, I'm going to go ahead and call this angle A here and angle C here still. What I've now shown is that those angles are the same as the angles inside of the triangle because they're alternate interior angles, which are congruent to each other as long as you have parallel lines, which you can construct a parallel line through point B that is actually parallel to AC. So that tells you that the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees. This right here is what the interior angle sum theorem for triangles is actually saying. And this is a proof of that. Now this is what I would call a hand-waving proof because I didn't actually write down all the justifications, like the fact that I used an alternate interior angle theorem or the like, or even the construction of a parallel line through a point, not on a line. There's rules that usually have to apply there as well. But this also is what the video is going to be displaying and demonstrating as well if you watch that in class. So I highly encourage you to click on the link for that in the slides, or to be able to watch it in class through one of your playback sessions. It's a really great video. It's only about 2 minutes, and he does a construction proof, or a proof by construction, where he uses transformations to prove the triangle angle sum theorem. I utilize parallel lines and alternate interior angles to justify that, and so that's kind of like a miniature proof of why it works the way that it does. In other words, all three angles are supplementary to each other because they're going to be adding up, or their sum is going to add up to 180 degrees. And with that said, we can actually use that information to figure out, if two angles are known in a triangle, what the third angle that's missing is. So take a moment to see if you can come up with the missing angle here at angle C. So in this particular case, you should have said 25 degrees. And easily to show that, we know that measure of angle C is going to equal 180 degrees minus the sum of the other angles that are provided, 30 and 125. So there we get 180 minus 155, and that's going to get us a 25 degree angle. So there we go. Now let's go ahead and take a look at an example where there's no illustration or diagram given, and yet I'm still going to be finding the value of x. Using the triangle angle sum theorem, one of the first things that we want to go ahead and do is we want to find x first. Just x. Now the reason we want to find x first is because it is not the measure of angle A, as that is what we're going to be finding down here, but x is actually a part of the measure of angle A, so by finding x you're going to be able to find A. And what we do is we take all three expressions for every angle, and all we have to do is just add them together. Now each expression is an algebraic expression, meaning it has variables and numerical values, but we know that they're just angles, and the sum of all the angles in a triangle has to equal 180. So highlighting this in green, 5x and 2x and 3x are like terms, and negative 25, positive 10, and positive 5 are like terms. So we can actually go ahead and combine those together. So we get a positive 10x for my variable terms, and then here we get negative 10 for my numerical terms. Then I can go ahead and simply add 10 to both sides, so I get 190. So I get 10x equals 190, and I can divide everything by 10, so that means I get 19. Now that I've actually found the value of x, the second step is to plug it in for the measure of A. So I'm going to go ahead and plug in for the measure of angle A. So the measure of angle A is going to equal 5 times 19 minus 25. So that's going to end up getting me 95 minus 25, so that is a 70 degree angle. So the measure of angle A is going to be 70 degrees in this case. Looking at this example here, we now have to find the measures of angles 1, 2, and 3. So the first thing I want to point out, and this is an important relationship that we've already discussed, but angles 1 and 2 are vertical angles, right? So we're going to use that in a moment, where we're going to find the measure of angle 1 now, doing the same thing we've been doing. When we have a triangle with two angles that we know and one that we don't, we can take 180 and subtract the difference of the other two, right? And the other two are 64 and 50. So there I'm going to get 66 degrees. So the measure of angle 1 is going to be a 66 degree angle. The measure of angle 1 is equal to the measure of angle 2. The reason why they're equal, remember, is because they're vertical angles. Because they're vertical angles, they are equal to each other. So since angle 1 is 66, that automatically means angle 2 is 66 degrees as well. Okay, so having said that, I now need to go ahead and find the measure of angle 3. But now if you look at where measure of angle 3 is located, I can see that 3 is the only angle that I currently don't know in that lower right triangle. So it's just like finding the measure of angle 1. I can take 180 and subtract the remaining angle values that I have, which are 55 and 66. And in that particular case, I get a 59 degree angle. So the measure of angle 3 is 59 degrees. The measure of angle 2 is 66 degrees, and the measure of angle 1 is 66 degrees. And those are the measures of all three of those particular angles. So now let's take a look at exterior angles for a moment. For the exterior angles, this is going to be an angle that is formed between one side of a polygon and the extension of an adjacent side, sometimes called an auxiliary side. And then, of course, you have to make sure you're looking outside of the polygon for that information, right? So the exterior portion is just this portion right here. That's the 150 degrees. This portion right here, of course, is the interior. And remember, when you look at the interior and the exterior, it's always going to be supplementary to each other, right? That's what actually this means right here. When we say supplementary, we're referring to their sum equals 180 degrees. So, that being said, let's take a look at an example of some exterior angles. We're going to look at angle 1 first. And if you look at angle 1, we want to look at the angle that forms a straight line with angle 1. This is not angle 7, but rather it is angle 8. You can see it forms a straight line with angle 1. Angle 8 is going to be the angle that does that. Angle 7 is vertical with angle 1. So you can't say that it forms a straight line with it. It's a vertical angle. If you look at angle 2 forms a straight line with both 4 and with 9. So angle 4 and angle 9 both form a straight line with that, which means those two angles, 4 and 9, are exterior to angle 2. And then likewise for this last bit, 3 forms a straight line with 6 and 5. So angle 5 and angle 6 form or are exterior to angle 3, or exterior to the whole figure, in fact. So all of those are exterior angles to that specific angle, meaning that they're all supplementary with that specific angle. So their sum would be equal to 180. So that leads to the exterior angle theorem. Okay, so if I take a moment to look at this diagram here, and let me just go ahead and copy this image. And then I'm going to go down and kind of show you the exterior angle theorem. So just very briefly, I want to show why this works the way that it does. So first of all, I know two things. One, I know that the sum of all the angles inside of the figure is going to equal 180 degrees. The reason I know that is because of the interior sum theorem we just talked about. However, I also know that angle 3 and 4, their sum is going to equal 180 degrees. The reason for why that actually is the case is because they form what we refer to as a linear pair, which basically means that they're going to be supplementary to each other. They're supplementary angles. They form a straight angle. They have to equal 180 when you add them together. So since both of these are actually equal to 180, I can actually just set them equal to each other. So the sum of angles 1, 2, and 3 equals the sum of 3 and angle 4. And what I can do is I can subtract angle 3 on both sides, canceling that out. And this gets me the measure of angle 1 plus the measure of angle 2 equal to the measure of angle 4. And that is exactly what this theorem is saying. It is saying that if you take both remote interior angles, which is again what these are, and you add them together, you are going to get this entire exterior angle value. That is what the exterior angle theorem is actually saying in the context of that particular problem. So having said that, that's kind of validated here with this graphic as well. Okay, so it is important to recognize a couple important features. Number one, an exterior angle is equal to the sum of the two remote interiors. And I'm going to really highlight that word remote. Remote means that it's further away, right? So we even have a whole statement on it. Remote interior angles are those that don't share a vertex or a corner of a triangle with that angle. Sometimes you might refer to it as the remote angles aren't touching the exterior angle at all. Okay, so please just keep that in mind as a reference for what makes a remote interior angle remote with respect to those angles that are exterior. So take a moment, pause, and see if you can come up with which angles are remote interior to angle 1. So you should have selected 5 and 6 because they have to be interior, number 1, so they have to be only angles 4, 5, or 6. And then 5 and 6 are the ones that are remote interior because they're not touching angle 1. They're not sharing a side with it. They're not sharing a vertex with it. So they're not adjacent to it the way that 4 is. So angle 5 and 6 are remote interior to angle 1 specifically. Angle 1 is the exterior. Now the exterior angle theorem says that the measure of angle 1 equals the measure of angle 5 plus the measure of angle 6, to be more specific. So that's what the exterior angle theorem says. And so now that I recognize that, I can actually utilize that information to help me figure out what the measure of angle 4 is. So in my case, I recognize that angles 3 and 1 are actually going to be remote interior to angle 4. Why? Because even though 4 is in its own little triangle here, 4 is actually exterior to the actual triangle here. So 4 is an exterior angle to that triangle, meaning that it has a value that's equal to the sum of the measure of angle 3 and the measure of angle 1. And so the measure of angle 4 is going to equal 53 degrees plus 26 degrees, which is 79 degrees. So I already know the measure of angle 4 is 79 degrees. And I could find measure of angle 2 in a couple ways, but I recognize that angle 2 forms a linear pair with 4. So I know that the measure of angle 2 plus the measure of angle 4 equals 180. So I can find the measure of angle 2 by simply subtracting the measure of angle 4 from 180, which I already found earlier in the previous step. So the measure of angle 2 has to be 101 degrees in this case. So there's actually a couple of ways that you could find the value of these angles. This is actually one way that I might do it based off of how I proved the exterior angle theorem earlier in the problem set. And that leads me to the final example here. The final example here is that I have to find the value of x. So we can see this is kind of a very straight shot exterior angle problem because you have these remote interior angles and you have that exterior angle. So what we know is that the exterior angle is equal to the sum of the remote interior angles. So notice how I'm just adding those together, and remember these are actual like terms because they're just constants. So I can go ahead and I can add those together to get 53. And then I'm going to go ahead at this point and I'm going to subtract 7x on both sides from the 13x. So I'm left with this 6x minus 1 equals 53. Then I'm going to add 1 to both sides, so I've got 6x equals 54. And then I can divide everything by 6, and I'm left with x equals 9. And that was all they were asking me for. However, I would point out that if I know that x is 9, what I could do with it is I could plug it in. For example, I could plug it in right here, and if I did that, then I have 7 times 9 plus 5. Well, that's going to be 68 degrees. So if this is 68 and that's 48 degrees, we know that combinationally when you add the two together, you get 116 degrees. That's the exterior angle value. So the real question for you is, how could I find this angle value then? Well, in that case, I would take 180 minus 116, and I get a 64 degree angle. So this is actually certainly one of the exit ticket helper questions, meaning it's a slide that can help you on the exit ticket when you're working with the exterior angle theorem. And so speaking of that, for the exit ticket, it's almost entirely kind of related to exterior angles in a way. So if you look at the example there on the left, I would refer to this slide right here as a helper slide for that particular question. And then the question in the middle there is asking for angle BAC. So in that case, given what they gave you, it's related to the exterior angle theorem. So any slide that gives you the exterior angle whatsoever is going to be extremely helpful for you when you're working with that. So this slide or this slide can be helpful in illustrating what to do with the middle question. And then the final question, I certainly would take a gander at this question again. Okay, one more time, because that's a great reference to have for your exit ticket right there for that final question, because it's asking for DBC or asking for angle C actually. So it's asking you for this angle right here. And then a little tip as well, by the way, when you're given angles of 3 letters, just remember that that is where the vertex is located at. So just be aware the middle letter is where the vertex is located at, and that can be extremely helpful for you. I would say the middle question actually goes really well with this slide. So I'm giving you a lot of tips there on what I would maybe look at, especially with the exit tickets that you have, and it really is focusing a lot on that particular theorem. And so that's going to be less than 4.04 for this unit.